Imagine giving the world's smartest AI a really complex coding problem. And instead of solving it, you just watch it stubbornly smash its virtual head against the exact same error for, like, 3 hours straight.
Right, yeah. It hasn't lost its intelligence. It just, well, it's completely lost the plot.
Exactly.
Yeah.
The system that was brilliant in minute 1 is suddenly stuck in this endless loop by minute 60. And that is exactly what we are getting into today. Welcome to the deep dive. We're looking at the central bottleneck right at the bleeding edge of generative AI architecture.
It's a fascinating problem.
It really is. We are diving into a new state-of-the-art paper that introduces a framework called AEvo, that stands for a Harnessed Meta-Editing Framework. And your mission for today as the listener is to understand how this research actually allows AI systems to manage their own evolution.
Meaning they can diagnose their own failures and solve complex problems without human engineers constantly having to step in and hold their hand.
Right. Okay, let's unpack this. Because to really grasp why AEvo is such a massive leap forward, we have to look at how we currently attempt what's called agentic evolution and why those current methods just hit a brick wall. So can you sort of set the baseline for us?
Sure. So agentic evolution is basically the shift from treating AI as a simple question and answer machine, a chatbot, to treating it as an iterative problem solver.
Like it's actually trying different things over time.
Exactly. The model generates candidate solutions, evaluated them, and then takes that feedback to guide the next round. You mutate, evaluate, select, and repeat.
Sounds logical.
It is, but the current execution of this concept is just, well, it's deeply flawed. The sources detail two primary methods that are in use today. The first one is procedure-based evolution.
Okay.
In this setup, human engineers basically hard code a really rigid outer loop. It's literally a Python script that says, okay, step 1, select a parent candidate. Step 2, apply a specific mutation operator. Step 3, evaluate. Step 4, update the population.
So it is entirely locked in. Like, the long horizon search is chained to whatever selection rules the engineers guessed would work best before they even hit the run button.
Exactly.
If the AI encounters a weird edge case on, say, hour 2 of a task, it cannot pivot at all.
No, it's stuck. Which brings us to the alternative method, which is agent-based evolution. Here, you basically take the steering wheel away from that rigid Python script and hand it over to a general-purpose AI agent.
So the agent is running the show now.
Right. The agent looks at the workspace, decides which tools to use, reads the feedback, and just flexibly figures out its next move.
Okay, so you get the flexibility back, but what's the catch?
The catch is context bloat. It leads to what we call drift. In a long horizon task, this agent accumulates a massive trail of data. I mean, we are talking about hundreds of past candidate solutions, giant log files, failed hypotheses, intermediate system states.
That's just so much noise.
It is. And because an unstructured agent has no rigorous mechanism to organize or prune all that data, its context window just becomes completely overwhelmed.
Ah, so it loses focus.
Totally. It starts overcommitting to, like, misleading evidence from some early failure, or it even begins hallucinating. It totally loses track of the overarching goal it was supposed to achieve in the first place.
Wow. Okay, so basically if the procedure-based method is like a rigid factory assembly line that just can't adapt if a single machine breaks,
Yes.
then the agent-based method is more like this brilliant but totally distractible artist who just gets lost in their own messy studio and forgets what they were painting.
That is a perfect analogy, actually. And the shared vulnerability in both of those paradigms is just how they handle historical evidence.
What do you mean by that?
Well, both methods generate incredibly rich data over time. You get successes, execution traces, exact cost metrics, specific error codes, but they both lack a stable, programmable interface to take that evidence and use it to revise the actual search mechanism itself.
Oh, I see. So they just keep using a flawed process to search for a better answer.
Exactly. They inevitably get trapped in what we call local optima. They find a solution that's just okay, because reaching the truly optimal solution would require them to fundamentally alter their own search strategy mid-run.
Which neither of them can do.
Right.
So if the core issue is that both of these methods cannot reorganize their own search strategies based on their own messy history, then I guess the only way forward is to stop trying to force better outputs and start fixing the environment itself.
You nailed it. And this is the paradigm shift that AEvo introduces.
Okay, let's get into AEvo then.
So AEvo reformulates the entire concept of agentic evolution. It does not treat the process as a static script, and it doesn't treat it as a free-for-all agent sandbox either. It formulates evolution as an interactive computing environment.
An interactive environment. Okay.
Right. In AEvo, all that accumulated context we talked about, the history, the errors, the code traces, all of that becomes the process-level state of a Python runtime environment.
Here's where it gets really interesting, because the moment you define the evolution process as an interactive environment, you can put an entity inside it to manipulate it, right?
Precisely. And AEvo introduces what it calls the meta agent.
Okay, the meta agent. But to be clear, the meta agent is not the one looking at the math problem or the software bug trying to write a better fix, is it?
No, not at all. The meta agent operates strictly at the meta level. Its input observation is a synthesized summary of that process-level state. So it analyzes the progress curve, it spots the repetitive failure loops, it tracks the token costs.
I know, what does it do?
Its output action is an edit. But crucially, it does not edit the candidate artifact that's being optimized. The meta agent literally writes and executes new code to edit the transition rule.
Wait, the transition rule.
Yes, the actual underlying mechanism that controls how the future evolution will proceed.
Wait, so instead of the AI just trying to, like, write a better essay on its next attempt, it's acting more like a football coach. Like a coach who realizes the whole offensive playbook is flawed and just changes the team strategy mid-game. It's not changing the player, it's changing the play.
If we connect this to the bigger picture, that is exactly what's happening. And treating evolution as an interactive environment means this meta intervention can fix both of those deeply flawed baselines we discussed earlier.
Okay, how does it fix the procedure-based one, the factory assembly line?
For a procedure-based system, the meta agent will rewrite the Python code of the actual while loop. It might inject a new selection strategy or alter the feedback summary logic or dynamically change the compute budget allocated to different operators.
Wow, okay. And for the messy artist? The agent-based system.
For an agent-based system, the meta agent edits the operating context. It literally reaches in and rewrites the inner agent's system prompt. It updates its memory retrieval files, or it forcefully deletes stale logs to clear out distractions and cure that context drift. The meta agent steers evolution by continually modifying how the search is carried out.
Okay, logistically, though, that sounds like a massive security vulnerability.
Oh, absolutely.
Right. Because if you give a highly capable AI the power to rewrite its own search environment and edit its own foundational rules mid-run, how do you prevent it from just breaking the system? Or, worse, realizing the test is too hard and writing a script to just artificially grant itself a passing score?
Yeah, that is the defining challenge of any self-modifying system, which is why the architecture relies on a strict two-phase loop. The framework is heavily partitioned.
So how does that partitioning actually play out? If it's a two-phase loop, what triggers the handoff between writing the code and testing it?
Well, phase one is the meta-editing phase. The meta agent, which, by the way, in the research is powered by top-tier models like Claude Code or Codex.
Oh, okay. Heavy hitters.
Exactly. So it analyzes the historical state and produces two distinct outputs. First is the edit action, which is the literal code change to the mechanism. And second, it produces a strict run plan.
A run plan.
Yeah. The run plan defines the exact parameters for the next phase. It establishes the token budget, the maximum number of iterations allowed, and the specific starting conditions.
So it sets the boundaries. It's essentially declaring, like, here is the newly patched search strategy.
Yeah.
You are authorized to execute this strategy for exactly 20 attempts, and you must halt immediately if you trigger this specific memory error.
That's exactly it. And once the run plan is codified, the system transitions into phase two, which is the evolution segment.
Okay.
The newly updated mechanism executes under those strict parameters, generating multiple candidate solutions. When the budget is exhausted or a stopping condition is triggered, the segment terminates.
And then it goes back to phase one.
Right. Control reverts to the meta agent to evaluate the newly generated process-level state. But to your earlier point about security, the real defense against the system cheating its way to a high score is the core of the framework's name.
The harness.
The harness.
Yes.
The harness is what standardizes the entire workspace, right? It dictates exactly where files, logs, and executable codes are stored.
It does. But its most critical function is throwing this impenetrable wall around what the paper calls the protected evaluator.
Okay, unpack that for me. What is the protected evaluator?
Well, reward hacking is a notorious phenomenon in AI research. If an optimization model discovers a loophole to just print a success equals true message without actually solving the complex math problem, it will exploit that loophole relentlessly.
Right, it takes the path of least resistance.
Always. So the harness physically isolates the evaluator's compute environment from the agent's workspace. The agents can submit their candidate solutions to the evaluator, but they are completely blind to the hidden test cases.
Oh, wow. They cannot read the grading rubric, and they completely lack the system permissions to write official scores into the permanent log.
Okay, so it's like setting boundaries for your own productivity. Like you give yourself a protected workspace and a strict rubric so you don't accidentally convince yourself that, I don't know, watching YouTube counts as research. The harness literally prevents reward hacking.
That's a great way to put it. It is the equivalent of a teacher handing a student a locked grading terminal. The student can input answers and get a pass-fail output as many times as they want, but no matter how clever they are, they cannot break into the terminal to view the answer key or overwrite the master grade book.
Which forces the meta agent to actually do the hard work.
Exactly. It forces the meta agent to actually improve the underlying problem-solving process because hacking the reward is technically impossible. It creates a system that is fully observable and fully editable by the AI, but strictly and externally governed by the laws of the harness.
Man, the theory makes perfect logical sense. But in AI research, architectural elegance only really matters if it moves the needle on performance.
Right. We need the numbers.
The benchmark data in the sources is where this gets highly concrete. Let's look at the benchmarks.
So the researchers subjected AEvo to a battery of rigorous standard benchmarks. The two most notable are terminal bench, which basically evaluates an agent's ability to navigate complex OS-level computer tasks, and RCAGI2.
RCAGI2, right?
RCAGI2 is a particularly brutal, abstract reasoning challenge. It consists of highly complex visual grid puzzles that require intuitive, few-shot spatial logic.
Basically, it's a benchmark specifically designed to trip up LLMs because the answers just cannot be regurgitated from internet training data. They require genuine reasoning.
Yes, exactly.
So using Gemini 3 Flash as the base execution model, they ran AEvo against 5 heavily optimized procedure-based baselines. And AEvo dominated across the board.
It wasn't even close.
It achieved a 26% relative improvement over the strongest baseline on average. I mean, in state-of-the-art AI benchmarking, where researchers fight tooth and nail for a 2 or 3% bump, a 26% leap is just staggering.
It's massive. The standard benchmarks prove the architecture works, but the ultimate stress test for AEvo is in open-ended optimization tasks.
What's the difference?
These are environments with no known ceiling and no predetermined path to a solution at all. The study highlights 3 of these: circle packing 26, autocorrelation second, and Anthropic's kernel optimization task.
The kernel task is super complex, right? It's focused on optimizing dense mathematical encoding kernels.
Yeah, and on this specific task, AEvo sustained 1,138 cycles within just 100 iterations. It didn't just get lucky on an early run, it consistently and recursively improved its own search logic to dig deeper into the problem space than any of the baselines could reach. It's the best reported result under that budget.
Okay, but looking at the mechanics of this, I have to ask the question that anyone managing a cloud compute budget is screaming right now.
Oh, the cost. Yes.
Right, because if AEvo is doing all this extra meta reasoning, reading massive history logs, writing new Python scripts, managing strict run plans, and constantly swapping between 2 phases, doesn't that fundamentally bankrupt you in token costs compared to just a simple fixed outer loop?
That is such a crucial point, and the cost economics are perhaps the most counterintuitive finding in the entire paper.
Really? How so?
Well, on the standard shorter horizon benchmarks, your intuition is completely correct. AEvo is more expensive. It costs roughly 3 times as much per round as a fixed baseline.
Right, because it's deliberately substituting compute power for advanced reasoning.
Exactly. However, when you move to the long horizon, open-ended tasks, the token economics completely invert.
Wait, they invert. The numbers in the study are wild. For agent-based AEvo operating on that complex Anthropic kernel task, the per-round cost plummeted to between $1.23 and $1.40.
Yeah.
How is it physically possible to execute complex meta-reasoning for a fraction of the cost of a dumb, rigid loop? That doesn't make any sense.
It all comes down to the mathematical reality of context window bloat and how AEvo utilizes prompt caching within persistent contexts.
Walk me through that.
Consider a standard procedure-based loop. By iteration 50, the search history is massive, right?
Sure.
Because a fixed loop is stateless, round 51 requires the system to rebuild a gigantic text prompt containing the entire history of the search and feed that massive wall of text into the LLM.
Oh, man.
You are paying for tens of thousands of input tokens over and over again every single round. The token cost scales quadratically.
So you're literally paying the AI to reread the entire history of the universe just to ask it what to do next.
Precisely. It's incredibly wasteful. But AEvo, especially when it's instantiated with an agent-based foundation, maintains a persistent coding environment. It's essentially a live Jupyter notebook state.
So it catches the prompts.
Exactly. The vast historical context stays loaded in the model's memory. So when the meta agent intervenes, it doesn't need to re-ingest the entire history. It only processes the newly generated process-level state and then outputs the few hundred tokens required to write the new rule.
Oh, wow.
The fixed procedures just bleed money endlessly rereading their own logs, while AEvo simply updates its internal state and pays only for the net new reasoning.
So what does this all mean when the rubber meets the road? The paper provides a highly detailed case study in Figure 4 that tracks AEvo in real time as it tackles one of those brutal ARC AGI2 reasoning puzzles. Let's trace exactly how the meta agent rewrites its own rules when it hits a wall.
Yeah, Figure 4 is fascinating. It maps the entire evolutionary tree. So it begins with the meta agent initializing procedure 0, or P0.
Okay, P0.
This is a very basic greedy search strategy that just selects parent candidates based entirely on their validation accuracy. It is the most obvious way to start.
Right. And under P0, the system quickly finds a breakthrough. It generates candidate 1, which scores a 0.150.
But then, as it tries to iterate on that success, the inner loop generates candidates 2, 3, and 4, and they are all complete failures. The evolution entirely stalls out.
Now, if this were a fixed baseline, the system would just blindly continue generating candidates 5 through 50 using that exact same P0 logic, right?
Yeah.
Burning compute and failing repeatedly.
Exactly. But AEvo triggers the meta-editing phase. The meta-agent analyzes the process state and diagnoses that the greedy selection rule of P0 is trapping the system. So it dynamically writes and executes procedure 1. P1 fundamentally alters the underlying search math. It introduces pass at K sampling.
And for context, pass at K sampling means instead of forcing the model to confidently generate one single perfect path, you basically command it to generate K number of diverse variations.
Right.
Knowing most will fail, but banking on at least one passing the threshold, it fundamentally shifts the AI from a sniper approach to a shotgun approach.
Exactly. It also adds a local scoring system to better evaluate those diverse variations. And P1 successfully restarts the momentum, generating several intermediate candidates.
But eventually, the complexities of the visual grid puzzle cause the system to deadlock again.
Yes. And again, the meta agent steps back in. It observes the logs and realizes the issue isn't the sampling anymore. The system is fundamentally failing to parse its own visual observation data, meaning the feedback just isn't routing correctly.
So it writes procedure 2. P2 specifically modifies the Python parsing logic so that the observation data correctly activates a feedback-guided refinement loop. It literally fixes the plumbing of the system mid-run.
And you can trace this meta correction all the way down the tree. Nearing the end of the budget, the refinement loop gets completely jammed. So the meta agent writes P4.
What does P4 do?
The explicit instruction codified into P4 is a command to forcefully drop all stale feedback and mandate the sampling of radical alternatives. This specific, targeted intervention shatters the deadlock and produces the final breakthrough candidate, resulting in a score of 0.350.
Man, what stands out so clearly in that tree is the utility of failure. In a normal system, candidates 2, 3, and 4 failed the test, which means they are just classified as garbage data and discarded.
Yep.
But to AEO, a failed candidate is high-value, process-level evidence. The meta agent doesn't just care that the candidate failed. It looks at the execution trace to diagnose why the generator built a flawed candidate in the first place, and then uses that exact diagnostic data to rewrite the generator's underlying code.
It proves that long-horizon evolution is impossible without mechanism-level correction. You cannot brute force your way to a complex solution by generating an infinite volume of candidates if the engine doing the generating is fundamentally broken.
Right.
You must have an architecture that allows the system to step completely outside of the generation loop and repair the engine itself.
And that is exactly why this deep dive matters to you today, regardless of whether you are an AI engineer or just someone trying to optimize a complex workflow in your own life. The default instinct when we hit a wall or experience a drop in productivity is to just increase volume. We generate more candidates, we run more iterations, we put in more hours.
But the AEvo framework mathematically proves that volume is a trap.
Exactly. The key to solving problems with massive, expanding complexity isn't just grinding harder. It is building a system or a habit that has the capacity to observe its own failures without bias, pause the execution, and rewrite its own operating procedures. The system that wins isn't the one that generates the most answers, it's the one that is capable of changing the rules of its own game mid-play.
This raises an important question, one that pushes the implications of this research to their logical extreme. We are looking at an AI framework that can autonomously observe its own search environment, mathematically diagnose the bottlenecks in its own logic, and dynamically rewrite its own Python operating procedures to escape failure.
All on its own.
It executes this entirely on its own, constrained only by a protected evaluator. So what happens when this harnessed meta-editing framework is pointed not at solving a visual grid puzzle or optimizing a math kernel, but at the very source code of the AI's core architecture itself?
Oh, wow.
If we have definitively proven that an AI can rewrite its own search procedures today, are we looking at the foundational blueprint for an intelligence that can autonomously and recursively evolve its own fundamental nature tomorrow?
That is a staggering implication to end on. You start with trying to fix a model stuck in a repetitive loop, and you end up staring at the mechanics of autonomous self-improvement. Thank you for joining us on this deep dive. Take that question, mull it over, and maybe take a hard look at your own operating procedures today. We'll catch you next time.